Doctor?
Okay. Yeah.
The previous lectures, that recording, you are not uploaded in the YouTube. I sent to you an
It's already
email,
on
but
YouTube.
maybe you didn't see it.
I saw it. It's already on YouTube. It went up.
No, the section after.
Yes. Which
In
section?
the YouTube, it is for. It's. I think it is from 4.1 for 4.3. So after that, you didn't upload it from 4.5. From 4.5. Yes.
Let's see. I go to Moodle, log in. General Physics 1. Week 5, Lecture 8, Lecture 9. Lecture 8, this is the YouTube link.
Okay.
4.4 to 4.5.
I checked it in the
And
previous time, but it is not.
Okay, it might be that I uploaded it after you checked it.
Okay, thank you.
Okay, but both of them, if you go to Moodle now, you will see both of them, Lecture 8 and Lecture 9. Both are there. Okay. So, the last thing we reached is the definition of mass. We'll be talking about mass and weight. Okay. Now you might notice that my order of introducing some things are slightly different than your book. I think it is better to do it this way because it makes it easier to understand. Okay. All right. So we reach to mass, quantity of matter. Elephant has a large mass, and a mouse would have a small mass. So far, so good. We know that. Now, what does this mass actually mean? This mass, usually we don't use the term mass, right? Usually we speak of weight. So, كم وزنك بالعربي? In English, we say, what's your weight? And we usually give it in kilograms. So, I'm very fat, so I'm 90 kilograms. I weigh 90 kilograms. Turns out, this actual, what we're doing is, we are mixing between two different concepts when it comes to physics. Because mass and weight in physics are actually not the same thing. It's very, very different. Okay, so let's take a look. What does mass mean? What is its effect before what it means? So we introduced Newton's second law, which says F equals ma. We'll explain it in a second. Okay, F is for force, and it is a vector. It has a unit of newtons, which 1 Newton equals 1 kilograms meters per second square. Okay, mass is in kilograms, and acceleration as well, acceleration. Now you already know what did I mean by saying that? We are confusing things, because usually I say my weight is in kilograms, and weight is a force. My mass can only be in kilograms, not my weight. So in component form, remember what we said all the way back in chapter 2 with vectors. The x, y, and z components are upset. They never speak to each other. And that was true when we were doing 1 dimension. That was true when we were doing 2 dimensions. And now it is also true when we do forces and Newton's laws, because again, these are all vectorial calculations. So whatever we learned in chapter 2 carries on here, okay? So force in the x-axis and the y-axis and the z-axis are upset with each other. They don't speak to each other. Each one of them is separate to the rest. Okay, so if we have a really complicated system, we can look at only one axis. So fx is max, Fy is may, and Fz is maz. Okay. Doctor, you said a lot of things, but you still haven't explained what really we're doing. Getting there. Now, force is what we said is what causes the change in velocity. Okay, remember our first rule, Newton's. Okay, I don't have it here. This was another slide. Remember when we said things are really lazy, and unless we force them to do something, then they don't do anything else? Well, this is what we mean by force. Now, if the net force on a body is 0, we start with the simplest thing. A body has no forces on it. Its acceleration is 0. Be very careful. Okay, be very careful, because what it says here is, okay, acceleration is 0, not velocity is 0. So it is very, very possible that something would be moving and still have a net force of 0 on it. Okay, only it's not going to change the velocity. We say if its acceleration is 0 and the net force on a body is 0, the forces and the body are in equilibrium. There might still be forces. We don't say there are no forces. We say they are in equilibrium, and this is why net force up here is underlined and in a red square. What do I mean by net force? Say, for example, in this photo, this person is pushing with a force of 10 newtons. This person is also pushing at 10 newtons, but in the opposite direction. Now, because force is a vector, my net force or force total will be equal to 10 in the plus I direction plus 10 in the minus I direction, which is the same as saying 10 minus 10, which is equal to 0 newtons. So the box doesn't move. And although we're writing it here in fancy terms, vectors I and j and force, we know this innately. We know this. We have seen it. If two people are pushing on something from opposite sides, nothing happens. If two people are pulling on something with exactly the equal force, then again, none of them get that thing. Okay. And equilibrium means, okay, they are equal. Okay. They are compensating for each other. Okay. Okay. Let's take a look here. Okay. So we said the rule is F equals ma, and this is called Newton's second law. It tells us that to get a certain amount of force, we need to multiply the mass of an object by the acceleration of the object. Otherwise known as, if I want to know how fast something will change its velocity, what is its acceleration, I need to look at the ratio between the force applied and the mass. So let's try an example. A constant horizontal force, F applied, is applied to block A of mass ma. So this block has a mass ma. The block slides over a frictionless surface as shown. What is the acceleration of the blocks? How do we determine how fast do the blocks move? Okay, so this is A, this is B, and this is C. Excellent. Everyone chose C, which is exactly what we mean, because the total force is equal to MA plus MA of A plus MBA, which is the same as saying, and since they're moving together, we will get this. So acceleration will be equal to F over the sum of masses. Okay, what is the net force? What is the force on block B from block A? Same A, B. Okay, so we have results all around the place, going all the way from A to D. Okay, let's take them one by one. Only block A is pushing on block B. So we already know this is not correct because the mass of B wouldn't be involved in any way. Since the mass of B wouldn't be involved in any way, this is also not possible. Now we only have two options. Either it gets the full force, or it gets the mass of A times the acceleration. Okay? I would say this is the answer. Since it is being pushed by block A, the force is going to be mass of A times the acceleration of A. Okay. Let's take another look. We have a drawing that shows a steel ball flying at a constant velocity from point A to point B. Now there is no gravity. Okay, no gravity. As the ball flies past point B for a very short time, a magnet exerts a force on it in the direction of the magnet. Which of the following trajectories does the ball follow beyond point B? Remember, it is very short. Yeah, this is an important bit. Very short. Okay, most of you said 2, and this is correct. So since there's a force upwards, this is wrong, and this is wrong. Since it's a very, very short amount of time, the force is going to be applied for very briefly. So it's barely going to go up. So 2 is correct. If we did not say very short, if we said ball flies past point B and the magnet is on at all times, no very short, then I would say 1 would have been a possibility. Okay. All right. Let's define something else. Let's define what we call a system. Okay, we'll do some numerical examples in a little bit. What is a system? A system consists of one or more bodies. Okay, what does that mean? What am I actually doing? Well, here's a system. It's a bunch of things connected together. Nothing really fancy. A whole bunch of wheels with 2 blocks. Okay. Now, any force on the bodies exerted by bodies outside what we define to be a system, we call an external force. Okay. Now we define what a system is. I could have easily said, this is my system, but I did not. what I said is my entire thing is my system. Okay, so anything that is affecting it outside the system is called an external force. What about forces between bodies inside the system? So for example, this wheel will have this block will have a force on this block, this block will have a force on this block, and so on and so forth. All of these are called internal forces. Now, what is the main difference between internal and external forces? Have you ever tried moving a car by simply moving inside it? Okay, so you're inside, never mind a car, complicated. A bicycle. When you were a child, or maybe you're still a bike hobbyist, okay, you're inside a bike and you try to move it. Not pedaling, just doing something like this and moving it. It's very difficult to move something when you're inside it. And the reason is, when you're inside it, you're part of the system. What you're doing is all internal forces. And that brings us to a very important rule. Only the forces that act on an object determines its motion. We only consider the forces that act on the object externally. Internal forces are not considered. So let's take an apple, which is being subject to multiple forces. What I did here, I drew the apple and I drew all the forces with their directions, is called a free body diagram. Okay, now you will notice that in your book, free body diagram is actually the very last thing that is done in this chapter. It is section 5.7. Okay, but I'm introducing it beforehand because I think it's important in what we're going to be doing in a bit. But first, it's 12:30. Okay. All right. Attendance has been taken. All right. So, where was I? Only the forces that act on an object determine its motion. Now we only consider the forces that act on the object itself. Sorry. Okay, joys of working from home. All right, let's go back to our presentation. Okay, free body diagram. What is it? It is a way to explain graphically what a problem is asking from us. Aywa. He's also doing, that was my son, and he's also doing online learning, but for first grade. So he's using the printer that I have here. Okay, so a free body diagram, I draw the body in question. Why is my thing stuck? I'm unable to see any comments. Okay, so I'll take an apple and I'll draw everything on it. Okay, these are my forces. I have F1, F2, F3, F4, whatever forces. I don't care what they are. Now, because if you are like me, artistically challenged, and drawing is very, very, very bad, we just draw it like this. I don't care how big the apple is or what the object is. It might be an apple, it might be a person, it might be an airplane, it might be an entire planet or a solar system, or it could be, you know, a car, an airplane. I will just draw a dot. This is my body. And here are all my forces. Now, the longer the line is, the bigger the force, usually. Okay, and the directions are given. Now, if we're being very, very accurate, we can do it exactly with the degrees and everything, but a sketch usually is all we need. Okay. Now, whenever we start solving a problem, we start doing it this way. Why? You will see in a bit that drawing a free body diagram is actually immensely helpful in understanding not only how one works, how a problem works, but also in making the problem much, much easier to solve. Okay, most humans are very visual people. We like to see what we are doing. Words and long sentences are not very, very useful. Okay, all right. Let's go to something different and then come back. Newton's third law of motion. I don't know if you have seen this. I grew up with Dai Shuja and Dragon Ball. Okay, I think this is Naruto or something. I don't know. I haven't seen this. Okay. Now, Newton's third law in English says when two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. Now, I have my own way of explaining Newton's third law. يا أخي رسوم فنان. زين. Which is what we usually say. Okay, لما كنا في الحارة نتضارب كان عندنا جملة. This is standard. Whenever a fight is about to start, you look at you look at the guy opposite you and you go, تضربني بضربك. Right? This is a basic rule. If you hit me, I'm gonna hit you back. And the way it usually works is, okay, the harder he hits me, the harder I'm gonna hit him. Okay? Now, there are three main things here. Okay? There is a condition. Okay? One, I'm only gonna hit him if he hits me. So it is conditional on a two-body interaction. There needs to be two bodies interacting for Newton's third law to take part. Okay? That's the first one. The second one is the forces are not going to be acting on the same person. It's going to be, or on the same object. It's going to be acting on two different bodies. Okay? Because, well, if he hits me, I'm not going to hit myself. I'm going to hit him. Okay? A very violent lecture today. Okay? So it's going to be acting on two different bodies. Okay? All right. What's the third rule? The harder he hits me, the harder I hit him. So overall, two bodies interact, forces are opposite in direction and equal in magnitude. Otherwise known as, for every action, there is an equal and opposite reaction. I prefer the Arabic version. Okay. Now, it is very important to realize that these forces act on different things. Okay, and thus they don't cancel. I'm going to draw the diagram, and then you're going to understand what I mean. Look at this person. This person is walking. You have two forces. Look at the free body diagram, okay? You have one force going this way, another force going this way. They are opposite in direction, and they are equal in magnitude. In the book, this is 5.5. Okay, Newton's third law, 5.5. Okay, so now some of you will come to me and say, but wait, you just told us a little bit ago that if I have a box and I have two forces on it in opposite directions, okay, then they cancel out. You just gave us an example where you did 10 minus 10 equals 0. But now you're telling me that these are two forces in opposite directions. They are equal, but then you're telling us that they don't cancel. So what gives? حدد موقفك. إما أنه they cancel or they don't cancel. The very key difference here is, okay, that in the box example, okay, the forces were being done on a single object. But here, the forces are on two different objects. FPG is the force exerted on the foot or on the person by the ground. So the force is on the foot. FGP is the force exerted on the ground by the person. So if I am drawing a free body diagram, okay, for the person's foot, okay, I am only going to have this. I am not going to have any other thing. On the other hand, if I do a free body diagram for the ground, I am only going to have this, FGP. Okay, I'm not going to have FPG. And this is why they don't cancel out. Let's do an example, and I really love this example because usually it drives both me and the students crazy. A 20-ton truck. No, this is not friction. This is not friction, ya mama. We haven't gone to friction yet. This is simply okay, the horizontal force exerted by the person's foot on the person's foot by the ground. This could be friction, but it does not need to be friction. Okay, so for example, let me give you another example before we move on. Say I have a table. Okay, say I have a table. Now I have a book on a table. Now this book, there are two forces acting here. One, there is gravity, so F equals mg on the book going down. And there is another force going up, which we will call the normal force, which I will explain in a little bit. So not friction. Okay. And these two forces are opposite to each other. Okay. But also, you have a force, which we call the third pair force of Newton, which is exactly equal to mg, but it is of the table acting on the block. Okay. Let's do the example, which will drive both of us crazy, and then things are going to be a tiny bit clearer. A 20-ton truck moving left hits a 0.1 gram butterfly. So to those of you who are not sure what a ton is, so 20 ton equals 20,000 kilograms, which is equal to 20 million grams. Okay, so a 20 million gram truck moving left hits a 0.1 gram butterfly. Which of the following is true? The truck's force on the butterfly is larger than the force of the butterfly on the truck. The truck's force on the butterfly is smaller than the force of the butterfly on the truck. Or C, both forces are equal. A few C's, a few A's. Okay, so we agree that this is not important. This is not going to work. Okay, so if we did a poll, I would usually find about 3 in 4 people telling me that A is correct, and only 1 in 4 people would tell me that both forces are equal. And the truth is, the correct answer is C. Both forces are equal. Now, I know your head is exploding, okay? How on earth can a 20-ton truck exert the exact same force as a 0.1 gram butterfly? Makes no sense. Okay, well, remember we said each action has an equal and opposite reaction. So when the 20-ton truck exerted this force on the butterfly, okay, the butterfly is going to exert the exact same force, but in the opposite direction on the truck. Now, the result of these two forces are very, very different because remember, F equals ma. Okay, so the A of the butterfly is going to be a very big force divided by a very tiny mass, which will give me a very, very big acceleration, right? It usually means that the poor butterfly is going to fly away dead for a few hundred meters. Okay. Now, the same force, which is in the opposite direction of the butterfly on the truck, will not have the same effect on the truck because, remember, the mass of the truck is really big. So acceleration of the truck is going to have to be the same big force, but also on a very large mass. Okay, so your acceleration is actually going to be very, very tiny. Okay, so the acceleration of the truck is going to be something like, minus 0.0000 something. So it's not even going to feel it. Okay, so although the forces are equal, their result is very, very different. Okay, let us actually do let's do something. No, the truck is not going to stop. The truck is not going to stop. Okay. Is this clear to you? Can you see the font clearly? Is it big enough? Okay. Let's try it out. Truck, butterfly. The mass of the butterfly is in grams, 0.1. Sorry, the mass of the butterfly is 0.1. The mass of the truck is 20 tons, kilograms, grams. A rather large number. Okay. Now we have force. We have acceleration. Let's say the force is, what kind of force do you want? Give me a number. Anyone give me a number. Remember, it's a truck hitting a butterfly, so it's really, really large. Something. If I just take it by weight, okay, which is not accurate, but I'll take it by weight. 9.81 times 20,000 kilograms, 196,200. Okay. Now, what is my acceleration going to be? Meters per second square. So this is what happens. If you have the same force, because they are opposite in opposite directions, okay, actually, let me do this. Okay, what is going to happen is, why is this accounting? Just give me general number. Okay, what actually happens is, okay, your butterfly will get a ridiculously large acceleration and it's going to be flying off in that direction, but the deceleration that you get from the truck, for the truck, is so tiny that in reality nothing really happens to the truck. Okay. نور كيف الكتلة ما لها علاقة أبدا بالقوة؟ We said F equals ma. Okay, this is what you mean. Okay, now I understand. Yeah. No, she means something different. She means something different, that they cancel out in the equations. Okay, so in Newton's laws, forces are the same. Okay, but remember, this is only possible because it's acting on two different bodies. Okay, so the butterfly is going to be flying away really, really far away, and the truck is gonna do, well, nothing, minus 0.01. Okay, here we have fixed the force. We know what the masses are, and we fixed the force. Okay, so since we fixed the force, accelerations are the only thing that can change, and you get a really, really large acceleration for the tiny object and a really, really small acceleration for the truck. Okay. Yes, Muhammad. كل ما زاد الوزن زادت القوة. But here you have fixed القوة. You have fixed the force. Okay. So if you have fixed the force, then, well, your only variable is acceleration. Okay. All right. So this is why I told you I really, really like this example, because usually it drives both me and pretty much all the students crazy. ليش نفس القوة? Because this is by definition. Okay, by definition, Newton's third law is for two objects opposite but equal. Let's see. Let's see if we can get a better explanation than what I am able to give from Wikipedia. Okay. There's another way to describe this, okay? And it might or it might not be easier for you to understand, which, let me get it out. Okay. Let's slow down. Let's try to explain this in a different way and then continue. Okay, let me ask you a question. We said that forces causes changes in motion, there's acceleration, there's a whole bunch of things, right? Okay. When I am pulling on a rope, why doesn't that rope break? Well, I am pulling on a rope. I am exerting a force. Why doesn't that rope break? Let's go to another thing. Here's a swimmer. She is pushing against a wall when swimming. Okay, why doesn't the wall move? Why doesn't the wall move? She pushed on the wall. Oh, sorry. My bad, I stopped the presentation. Now you should see it. Here's a swimmer. She is pushing against a wall while swimming. Now, why is the wall not moving? she pushed on the wall, so there's a force there, and we said whenever there is a force, F equals ma, there is an acceleration. Why doesn't the wall move? Okay. القوة ما كافية لتحريك الجدار. Okay. Okay, that's good. That's good. Now, why, though, does the swimmer end up propelled to the other direction? Two things happen, right? The wall doesn't move, but she ends up pushing herself in the opposite direction. Think about it. I'll give you a minute. Okay. I see many replies and many examples. Here is what happens. You have the swimmer, and she is pushing against a wall. You have a wall, and the wall is actually also, by Newton's third law, pushing on the swimmer. Now, these two don't cancel out because they are acting on different bodies. But so far, we have been speaking about Newton's second law as F equals ma, correct? There's actually another way of explaining Newton's second law, okay? And this is actually how Newton initially stated his second law, and it is in terms of momentum. What Newton said was the instantaneous rate at which a body's momentum changes is equal to the net force acting on the body. And he said F equals dp by dt. Okay. So Newton's second law addresses this central question. What causes a change in motion of an object? Okay. So momentum was described by Newton as quantity of motion, how much motion there is, how much movement there is, a way of bringing together both the velocity of an object and its mass. Okay. We will be discussing momentum in detail later on, but for the time being, let us define the momentum. So force is ma, momentum is mv. Okay. Now, why am I bringing this up? I have mixed up all my pages. It's going to be a pain to fix later on, but never mind. I will find it. Give me a second. Okay, here we go. So there are two ways to take a look at this. One is through F equals ma. Another is through P equals mv, momentum. Okay. We cannot control the mass of either the truck or the butterfly. Okay. Their mass is fixed. They have certain velocities. Okay. Which means they will have different momenta. So say, for example, the truck is moving at, this is going to confuse you even more, introducing momentum at this point. Let's stick to F equals ma. We have an equation with three variables: force, mass, acceleration. We cannot do anything about force. It is fixed. About mass, we have force and we have acceleration. Okay, we need to fix another one of these. Okay, now since this is a collision, the force of the collision is going to be fixed by some other thing. Okay, the force of the collision is going to be fixed by a different thing, by our rate of change of momentum. Yeah, we said F is also equal to dp by dt. So how quickly our velocity changes, also known as acceleration, is what defines our force. Now, how much will the velocity of the truck change because of this collision? Can you help me with this? Will the velocity of the truck change at all, or even a tiny bit? Anyone? Okay, 0.1. But in general, we agree that it's going to change a very, very tiny amount, correct? It's not really going to be changing a lot. If any, it's going to have a very, very, very tiny change. Okay. But the velocity of the butterfly, we agreed, is going to be changing a lot. Okay. So we fix the force. It's not that we are fixing it because we are giving some random number. It's because how quickly their velocity changes. So if their velocity changes at a certain rate, we can calculate that rate. We can find what the force is. The important point is that if we have the same force for two different bodies, the accelerations we get are very, very different for equal forces. But by definition, Newton's third law has the forces equal in magnitude and opposite in direction. I will try to come up with a different way to explain this, which makes more sense. But for the time being, we can just think of it as a rule. Yes, exactly, Muhammad. Exactly. Exactly. Okay. Now, let's introduce a bit of a catalog. Okay. Different types of forces, and then in the next chapter we can sort of, explore them further. Common forces. What are some of the most common forces that we see on a day-to-day basis? First thing, gravitational force, something that we all experience at all times. And we have already addressed it in one way or another in our free fall. Any object experiences gravity. Yeah, it's pulled by gravity. Now, gravitational force is given by, well, F equals ma, where A here is gravitational acceleration. So just like we did in free fall, where we use G for A, F equals mg. Okay? Gravitational force. Very simple. And this is usually what we call this Fg is called weight. Okay? So far, so good. Normal force, another type. Normal force, I have already said it once when I gave the example of a book on a table. Now, any object on some table, okay, or on a horizontal surface, will face the normal force. What is it? Say we have a block on a table. This block has a force downwards, that is Fg, weight, right? Now, why does this block not go through the table? Okay, why does it stay on the table? This pen is on my hand, okay, and it's experiencing a force downwards. Why is it not going through my hand? Why is it still here? Because my hand, okay, because it also experiences another force, which is my hand pushing it upwards, which is what we call the normal force. Now, these two forces both act on the block, on the same object, so they do cancel out, and we end up with this thing just remaining on the table or on my hand. Friction. Many of you know friction. Okay, pretty much everyone knows friction. If I am trying to slide an object, if two things are in contact with each other and one thing is sliding over the other, okay, this friction, there's something opposing this motion. Okay, this force that is opposing this motion, that usually slows it down or causes heat or whatever, we call it friction, and it always works in the opposite direction of motion. Now, I'm only stating these without going into a lot of details because we will be discussing in the next chapter and the one after it each one of these in detail. Tension. Now, if I have a rope and I am pulling on a rope, okay, the rope does not break. One of the reasons is because the rope has a certain property which we call tension. Okay, the rope pulls back on my hand. If I pull a rope, the rope also pulls back. Okay, and this is why whenever you pull on a rope, it becomes very tight. Okay, it has tension. Let's look at an example problem and see how we can use all of these together. cord is another word for rope, pulls a box of biscuits up along a frictionless plane. So I will underline some important things. Pulls up frictionless plane inclined at angle theta equals 30 degrees. The box has mass of m equals 5 kilogram, and the force from the cord has a magnitude of tension equals 25 newtons. What is the box's acceleration along the inclined plane? Well, first thing first, what do? We draw a free body diagram. I have my gravitational force, which is always down. I have my tension of the cord, which is in this direction. And I have my normal force here. What other types of forces do I have? Do I have tension? Do I have a friction? No, because the problem said it's a frictionless plane. If I had friction, I would have added friction. For the time being, I don't have any friction, so I'm going to be leaving it out. Okay, I'll do another example of friction later. Well, I have my angle here, theta, which I know to be equal to 30 degrees. Now, what do is I need to find the components, because these are not all acting in the x and y axes, are they? They're acting in different directions. Now, if I look at, let me actually go back here. If I look at this, okay, my x-axis is here, and my y-axis is here. So my only force that is acting nicely is gravity, and I have two forces acting at angles. So I can find the x and y component of tension and x and y component of normal force. Or what I can do, which makes it easier for me, is I say, you know what? Instead of this, I am going to say, this is my x-axis, and this is my y-axis. What changed now? My tension suddenly became very nice. It only acts in the x-axis. And my normal force also became very nice. It only acts in the y-axis. The only force now, which is not nice, is gravitational force, because it acts at an angle. Now, what I can do is exactly the same thing, okay? But instead of taking the components of t and taking the components of n, so this is 4 operations, I will only take the components of g, of gravitational, of fg, and that would mean only 2 operations. Okay, so I'll use the complementary angle. Okay, I'll use the complementary angle rules, and what I will do is I will take the components of the gravitational force. So in my new x-axis, remember, my new x-axis looks like this. My new axes look like these, x, y. So in my new x-axis, my gravitational pull is minus mg sine theta, and my new y-axis component of gravitational pull is minus mg cosine theta. Okay. Now we want to find the acceleration, right? The net force determines acceleration, F equals ma. Well, our forces in the y-axis balance, Fn equals mg cosine theta. And if you don't believe me, you can actually do the calculation, and you will see that mg equals cosine theta. Mg cosine theta is equal to Fn. Okay, so they cancel out. There's nothing. And we already know that because the block isn't flying anywhere, or is it pushing down anywhere. So we know that there's no net force in the y-axis. In the x-axis, though, we have tension going up, 25 newtons, and we have this going down, mg sine theta. So the sum of my forces, is equal to tension minus mg sine theta is equal to ma. And now all I need to do is do 25 minus, what was it? What was the math? 3 kilograms? I don't remember anymore. 5 kilograms, 30 degrees. So 25 minus 5 times 9.81 sine 30 is equal to 5a. And if I rearrange the equation, I will get acceleration equals 0.1 meters per second squared. No, Yamama, the speed is not constant because they told us that it is accelerating. And if we actually look at the balance of forces, we will see that mg sine theta, so 5 times 9.81 times sine 30 is actually 24.525. So we have, so our forces are not balanced. We have 25 going one side, 24.525. Okay, and that means there's an imbalance of forces. We have more force in one direction than the other. So my net is not 0, which means there's an acceleration. So the speed is not constant. It is changing. Ryan, yes, 0.095. 0.1 is rounded to 1 decimal place. Okay, sorry, to 1 significant figure. So to be very specific, this is 0.095 meters per second square. Okay. Let me see something. Okay, so it's 122. This is a really good example, which I want to do with you, man on scale on an elevator. But it will take a bit of time and I don't want to rush it. So what we're going to be doing is I will do this in the beginning of the next lecture. Okay, I will do this at the beginning of next lecture. إذا ما ساكن ولا هو يمشي بسرعة ثابتة. We're not saying the forces are equal. We're finding what the net force is. So see, what we're doing is we're not saying the forces are equal. We're saying we have a force that's going up and we have a force that's going down. Let us find out if it is equal or not. We have here 3 options. Okay, we have a force. I will redraw it. We have a force in this direction, and we have another force in this direction. Okay, now this is F1, and this is F2. Now we have 3 options here. Okay, if F1 equals F2, then F1 minus F2 will be equal to 0. Here we go. Okay, we have 2 forces, F1, F2. Now we have 3 options here. If F1 equals F2, okay, can you see it now, Marwan? Yeah, I keep forgetting to show the screen, sorry. Okay, if F1 is equal to F2, then F1 minus F2, or actually F1 plus F2, okay, will be equal to 0. Okay, and this will give us two options. We know our main rule is F equals MA. All right, so if our F is equal to 0, we have 0 equals MA, which means our acceleration is also 0 because we know there is a mass. Okay, now if acceleration is equal to 0, we have two options. Body does not move, or body moves at constant velocity. Acceleration is 0. That does not mean that it's not moving. If it's not moving, then acceleration is 0 means it will not move. If it's already moving, then acceleration 0 means it will continue moving at whatever velocity it was at. But we have another case. If F1 is not equal to F2, then F1 plus F2 is not equal to 0, which means that MA is not equal to 0, which means we have an acceleration. Now, again, we have two options. If my acceleration is more than 0, then body speeds up. Yes, sir. And if my acceleration is less than 0, then body slows down. So what we're actually doing here is we're not saying that they are equal. We are looking to see if they are equal or not, because sum of F equals MA. So the only way to know what the velocity is or what the acceleration is or whether it's changing or not is to find whether the sum of forces is 0 or not. The lecture is over, by the way. If anyone wants to leave, you're free to do so. I'll stay for about 10 more minutes to answer questions, and then I will leave too. So, any other questions?
دكتور
Yes.
دكتور الكويز بيكون الأسبوع الجاي يوم الخميس؟
أيوة، دائما يوم الخميس.
بيكون إجازة زين مال مولد النبوي.
هذه مشكلة الإجازات. Okay. Course information, work plan. فصل خريف دائما في واجد إجازات. اوكي، بيكون في إجازة مع مولد النبوي. اوكي، عندنا two options. اوكي، عندنا option نشوف له يوم ثاني، انزين، او عندنا option انه يكون نخليه يوم الخميس، ما نغيره، كيف ما هو. اوكي انا I'll do a poll. زين، دقيقة خليني اوقف recording.